symbolized using capital M. Now, whenever you want to read the data or write the data, the most important thing is you need to specify the address. From which memory unit you are reading the data, right? In the same way, when you are writing the data into the memory, into which memory location you are adding the data, the address needs to be specified, right? Let us consider here. I already told you in the first class itself, there exist different types of registers in our computer system. Something like memory address register, data register, instruction register, program counter, accumulator, and so on. Right? Now assume that here we have a register called AR. AR means address register. What data will be stored in this address register? The address of the memory component. When you are performing the read operation, from which memory location you are reading the data, that address needs to be there in the AR. That address is to be there in the address register. In the same way, when you are writing something into the memory, into which memory location you want to write the data, again the address is to be specified at the address register. That is the reason we are using this address register. Now see here, we are using one more register called as DR, which means data register. This data register holds the content of the content, whatever you want to read or whatever you are writing into the memory. The content is present in the data register. The memory location, the address of the memory component is present in the address register. Now see here how read operation is performed. When you are reading the data, what is required? You are reading the data, whatever the data is read, that is to be placed into the data register. Whatever the data is read is to be placed into the data register. Right? Before you read the data, first of all we should know from which location you are reading the data. Obviously, the location or the address of that memory component is there in the address register, and here we always use the letter M to specify the memory word. So, whatever the data is present at the memory word specified by this address register, assume that the value of AR is something like 100. That means whatever the memory word is present at the specified address, that is at 100th location of your memory component, is read, and that content will be moved into the data register. This is known as read operation. Right? So specify the address from where you are reading the data and get the data from that address location and move the data into the data register. Next we'll see the write operation. When you are writing, again same thing, you need to specify into which memory location you are writing the data, right? So here that address needs to be specified in the address register. Here I want to place the content present in the register R1 into some location of your memory component, right? Assume that the address value, AR value equal to something like 123. I want to place the content of R1 into the location 123, memory location 123. How this write operation is written? Content of R1 needs to be placed into the memory word of address register. That means R1 content will be moved into 123rd location of your memory component. Right? This is your memory unit, and this address register is responsible for getting the address location from where you are reading or into which location you are writing. So you will perform both read operation as as well as write operation on this memory unit. By using this, when you are performing the read operation, the data will come out of the memory unit. When you are performing the write operation, the data will be written into the memory unit. These are the two main operations that can be performed on a memory unit of your computer system. Now we'll see the arithmetic micro operation. So what micro operation is? The operation that is performed on the data stored in the register. We have four different types of micro operations: register transfer micro operation, arithmetic, logic, and shift micro operation. Register transfer operation is simple. We are just moving the content of the register from one register into the another register. In case of register transfer operation, you are not going to change the content of the register. The data will not be modified. Just we are moving the content from one register to the another register. Next, we'll see the arithmetic micro operation. Arithmetic micro operation, here the different arithmetic operations can be performed on the data present in the register. Now, what are different arithmetic micro operation? Different arithmetic operations are like addition, subtraction, increment, decrement, and shift. These are the basic arithmetic micro operations that you can perform on the register's data. First we'll see addition operation, next subtraction, and remaining operation we'll see. How we'll specify how you will specify this addition, subtraction, and so on. Whatever the basic arithmetic micro operations we have, how to specify this? Let us consider the example. If I have a instruction something like R3 to R1 plus R2. This micro operation specifies the add micro operation. Add micro operation. What data is added? It is adding the content of R1 and the content of R2, and the result is placed in a register R3, or the sum is placed in R3. This is what the add arithmetic micro operation. Next is subtraction operation. Generally, in our digital computers, subtraction is not performed directly by using the minus operator as we did decimal subtraction. So, binary subtraction is always performed by using the addition itself. Subtraction is also performed by using addition. We'll see how to perform the subtraction by using, I'll explain later. So how to specify this? R3 tends to R1 minus R2, which means that content of R2 is subtracted from the content of R1 and the difference is placed into the register R3. This is what the meaning of this register micro operation. R3 tends to R1 minus R2. Now let us see how to perform this subtraction operation. So here subtraction operation is performed by using complement as well as addition. Complement and addition. You can write R1 minus R2 equivalent to R1 plus R2 bar plus 1. I'll explain each and what is R2 bar, what is this addition, everything. Right? So just remember this subtraction can be performed by using the add operation as well as the complement operation. Now we'll see what is this R2 bar. You can write this R2 bar like this, or you can give a bar symbol just above this register. Both are equivalent. R2 bar means it is the ones complement of your register R2. R2 bar means ones complement of the register R2. Now R2 bar plus 1, which means that adding 1 to the ones complement of R2, and this is, this total we'll call it as a 2's complement, right? So R2 bar means the ones complement I'll tell you how to calculate 1's complement and 2's complement. Just remember that R2 bar means it is the complemented value R2 bar plus 1, which means that adding a single digit 1 to the 1's complement, which will give you the 2's complement of R2. Right? Now we'll see the add micro operation. Once again. Right. So what are the different arithmetic operations that can be performed? If the arithmetic operation is something like R1 plus R2, it represents an add micro operation. That means R1 content is added to R2 and the result is transferred to R3. Next, if the micro operation is something like R1 minus R2, which means that R1 is subtracted from R2 and the result is again transferred to R3. Next, R2 complement means what? R2 tends to R2 complement means complementing the content of the register R2, which is equivalent to 1's complement. Complement is nothing but just changing the values. If it is 1, change it to 0. If it is 0, change it to 1. That is what a complement means. Next, R2 complement plus 1. That means adding a 1 to the 1's complement, which is equivalent to the 2's complement of R2. Next, R1 plus R2 complement plus 1 is the 2's complement. So, here you can perform this subtraction R1 minus R2 by using this 2's complement and addition. So, both R1 minus R2 and R1 plus R2 bar plus 1 are equal. Both performs only the subtraction operation. And the next one is, if you add a 1 to the content of this register R1, then it means that you are performing the increment operation. In the same way, if you subtract a 1 from R1, it means performing the decrement operation. Adding 1 is increment operation. Subtracting 1 is your decrement operation. Before we move on to arithmetic micro operation, we need to know how the binary addition and binary subtraction are to be done. Once you know how to perform the binary addition, you can easily calculate binary subtraction. Why? Because we are not using the, we are performing the subtraction operation just by making use of complements and addition. We are not following any subtracting rules. Anyway, I'll explain the subtracting rules also, but that will not be followed in our digital computers. So, these are the rules to perform the binary addition. When you add a 0 and 0, the result or the sum is 0 and it leaves a carry of 0. That means no carry. In the same way, if you add a 0 and 1, it gives a sum of 1 and a 0 carry. 1 and 0 is same. It gives a sum of 1 and a carry of 0. When you add 1 and 1, then the result is 0 and it gives a carry as 1. This is different. 1 and 1. When you add 1 and 1, the sum is 0 and the carry is 1. Let us see the example. Here I want to perform the binary addition. Binary addition of these two register bits. One register is having the content 11101 and the other register is having the content 11011. Now see how this addition is performed. Binary addition is performed. See the rules of binary addition and perform this arithmetic add operation. 1 plus 1. 1 plus 1. When you perform 1 plus 1, what will be the result? The result is 0 and a carry of 1. It gives a carry of 1. The carry is 1. Now, next bits are 0 and 1. So, here we have a carry. So, perform the add operation on 1 and 0 first. 1 and 0 means what? 1 and 0 is, it gives a sum of 1 and a carry of 0. So the result is 1. Now that 1 is to be added to the bit 1. 1 plus 1, the result is 0, gives a carry of 1. Next, 1 and 1. This 1 carry 1 and the register bit 1. It gives a sum of 0 and a carry of 1. The sum is 0. That 0 should be again added to this 0. It gives a 0 as your result. When you add this 1 and 1, it is giving you a sum of 1. Sorry, carry of 1. Next, 1 and 1. The result is 0 and a carry of 1. 0 plus 1 is 1. Next, 1 plus 1 is again 0 and it gives a carry of 1. This is your carry. After this, you don't have any of the bits. So, you will write your carry here. Next, 0 plus 1 is again 1. This is the result of the addition operation by using this binary addition rules. In the same way, let's see how to perform the binary subtraction just by using the minus operator. Anyway, we don't use this, just we need to know what are the rules. So when you subtract a 0 from 0, the result is 0 and it gives a borrow of 0. When you subtract a 1 from 0, the result is 1. The difference is 1 with a borrow of 1. Similarly, when you subtract a 0 from 1, the result is 1 or the difference is 1 with a borrow of 0. And when you subtract 1 from 1, the result as well as the borrow, both are 0 only. So when you see this here, 1 minus 0, the result is 1. 1 minus 1, the result is 0. Next, 0 minus 0, the result is 0. The result is 1. 0 minus 0, the result is 0. Using this subtraction, we perform the ones complement, twos complement. Without knowing this ones complement and twos complement, you cannot construct, cannot go to the my operation in the first complement. Complement is just bits from 0 to 1. 0 is to be changed to 1. If you find 0, that's to 1. 5 should be converted to 0. When you see this example, find out the ones complement of this number 110. What? How to calculate the ones complement? Just inverting the bits. 1 is to be converted to 0, 0 to be 1. So the ones complement is 1 should be converted to 0. Next 0. Here the bit is 0. It should be to 1. 0, 1, 0, 1. This is variable. Ones complement is just changing bits. Next, so how to complement? If you add a 1 to the 1's complement. And the 1's complement will give you 2's complement. Example, calculate when the 1's complement, that is the 1 plus is 1 given answer. Okay. Sorry. Okay. Any complement, huh? Okay. One more example for 1's complement and 2's complement is 1's complement is just changing the bits from 1 to 0 and 0 is to change it to 1. Consider this example 1001101. What is inverted bit? Your inverted bit will give 1's complement. So this one is to be converted to 0. 0 to 1, 0, 0 to 0, 0 to 1, 1 to 2. This is you content of the number. Move on to 2's complement. 2's complement means what? Adding a 1 to the 1's complement. Adding a 1 to 1's complement is called as 2 complement. The given number 1001101, you have already corresponding 1's complement. Yes. So the 1's complement is inverting the bits, and 2's complement is adding a 1 to the 1's complement. So in this example, the 1's complement for the given number is this one. And when you add a 1 to this 1's complement, the result will be your 2's complement. 0 plus 1 is 1 with a carry as 0. 0 plus 1 is 1, and the remaining bits you can write as it is. Why? Because you don't have any bits to be added. So this is your 2's complement. Next. Now we know how to calculate the 1's complement and the 2's complement. Now we'll see how to perform this binary arithmetic operations in our digital computer. As of now, we have seen how to perform this addition as well as subtraction operations theoretically. The performance we have seen, but how this is done, what hardware components are useful to perform this, all that we'll see now. So, what are the main hardware components required to perform this binary addition operation? First, we'll see the addition operation. What are the hardware components required? So, it requires a full adder. The hardware component required to perform this addition operation in the computer system is a full adder. Now, what do you mean by full adder? It is a digital circuit. The full adder is a digital circuit. What it will do? It will perform the arithmetic sum of two bits. Arithmetic sum of two bits and a previous carry. It is the role of full adder. So what this full adder will do? It is a digital circuit. What it will do? It will perform the arithmetic sum, addition of only two bits. And if there is a carry, the addition of two bits plus carry is performed by full adder. Next is the binary adder. It is a digital circuit. Binary adder is a digital circuit. What it will do? It will generate the sum. Full adder will perform the sum of the two bits. Once the addition of two bits is done, it is going to give a sum and a carry, right? So this binary adder is responsible for generating the sum of the two bits, sum of the two binary numbers of any length. If you consider, if you are adding two bits or two binary numbers of length sum 5 by 5. Register 1 is having 5 bits. Register 2 is also having 5 bits. Then your full adder will perform the addition operation on only 2 bits at a time. It will consider 1 bit from R1 and 1 bit from R2, and the addition of those 2 bits is done by the full adder. Once the addition of all the bits, all the 5 bits of R1 and R2 are done, binary adder is responsible for giving the resultant. It is responsible for giving the sum value. Now, the binary adder is constructed by using is full adder, and these full adders are connected in cascade such that output of one full adder is given as an input to the next full adder. Output of one full adder is given as input to the next full adder. Output of second full adder is giving as input to the third full adder, and so on. So generally a full adder will contains, it will take 3 inputs and it will give 2 outputs. Any full adder will take 3 inputs and 2 outputs. Coming to this binary adder, to perform binary addition, what are the 3 inputs given are? The 3 inputs given to this binary adder are the 2 bits of the register. If you are adding R1 and R2, the bit from R1 is one input to the full adder. The bit from R2 is the second input to the full adder, and the third input is your carry input. Because one output of one full adder we are giving as a input to the next full adder, that is your carry value, right? And this full adder is giving you the 2 outputs. What are those 2 outputs? When you perform addition of 2 bits, you will get a sum value, as sometimes you will get a carry value. Those are the 2 outputs of the full adder. So one is sum and the second one is carry. This carry output is given as an input to the next full adder. This is the logic circuit for binary full adder. Here I am performing 4-bit binary adder. So I require 4 full adders. First full adder to perform the binary addition of the first bits of the 2 registers A and B. I am considering the 2 registers A and B. The bits of A are A0 to A3. The bits in the register B are B0 to B3. Right? So every full adder will take 3 inputs and it will give 2 outputs. First full adder, what is the input given to the first full adder? First bit of the register A and the first bit of the register B, and by default the input, the carry value given as an input to the first full adder is 0. I'll tell you why this C0 is 0. Next, this full adder is giving you two outputs. One is the sum value and the next one is the carry value, right? So a sum S0 is given and a carry C1 is also generated from the first full adder, and this carry of first full adder is given as an input to the next full adder, that is to your second full adder. What is the input to the second full adder? A1, which is the second bit of register A, B1, which is the second bit of register B. So these are the two bits, and one more input is coming from the previous full adder, which is the output of the previous full adder, that is C1. These are the three inputs of second full adder. It again giving you two outputs. One is the sum and the second one is carry. This carry is again given as input to the next full adder. In this way, the full adders were connected to all the 4 bits of the registers. Now we'll see. Let us consider that these are the two register bits. Assume that this is A register. This is the content of register B. I want to perform the addition operation on these two registers A and B. See here. This is A0, A1, A2, A3 and A4, B0 to B4. Initially, the value of C0 is 0. Why? Because when you are performing the addition operation on the LSB bits, LSB means least significant bits. So when you are performing addition on LSB bits of register A and B, you are just considering only 2 bits. Why? Because for the first bit, you don't have any carry. It will not generate any carry. Once you perform the addition of LSB bits, then only it may generate a carry as 0 or 1. Right? So that is the reason for the first full adder, the carry input is 0. C0 is always 0 for the first full adder. Right? So A0 is equivalent to 1. B0 is equivalent to 1. When you perform A0 plus C0, when you perform A0 plus Z0, when you perform A0 plus C0, what will be the result? Your sum S0 is 0 and it will generate, it is giving you a carry of C1 as 1. Now, what are the two inputs of the second full adder? A1 and B1. A1 and B1. What is A1? 0. B1 is your 1. So the second bits of the register A and B are given as input. So when you perform the addition on the LSB bits of A and B, if you get an output carry, we are giving that carry as output as a input to perform the addition of the next bits of the register A and B. So this C1, which is 1, is given as input to the next full adder. So again perform A1 plus B1 plus C1, that is 0 plus 1 plus 1, which again gives a sum S1 as 0 and a carry as C2, which is equal to 1. Again perform A2 plus B2, that is A1 plus 0 plus C2, which is carry, that is 1. It again gives a sum S2, which is equal to 0 and generates a carry as C3. In this way, until and unless all the bits of register A and B are done, you need to perform this binary addition operation using this full adder. Here we are when you have 5 bits in your register, you need to have 5 full adders. If the number of bits in the register are 3 full adders are sufficient. Next, we'll see how to perform the subtraction operation using the complement. We have already seen by using the 2's complement, you can perform. Now we'll see implementation of the digital subtraction operation. Here also we again require the full adders. Why? Because full adder is responsible for what? It is responsible for performing the addition of the 2 bits. So here we are implementing this subtraction by using addition itself. Therefore, you require again full adders. So full adders. When you are using the registers of 4 bits, you need 4 full adders. What are the inputs? Again, full adder, your full adder should have 3 inputs and it will generate 2 output. 3 inputs should be given, it will give 2 output. Output of one full adder will be given as input to the next full adder, right? So what are the inputs to the full adder? Here again I am considering 2 registers A and B. A register is having bits from A0 to A3. B register is having bits from B0 to B3. Along with full adder, we are going to use the XOR gate. One more basic gate, which is XOR gate. So one input to the full adder is the direct input. That is, the bits of the register A are given as a direct input to the direct input to the full adder. That is the first input. A0 for one input to first full adder, A1, A2 and A3. Next, second input is to the full adder is the output of the XOR gate. The second input of full adder is the output of your XOR gate. XOR gate output you are giving as an input to the full adder means you need to provide some input to your XOR gate. What is that input? Now, the input to your XOR gate is one input to the XOR gate is the direct input, that is the bits of the register B. B0 is one input to the first XOR gate, B1, B2 and B3. So, one input to the XOR gate is the bits of the register B. One input to the full adder is the bits of the register A. Second input to the full adder is the output of XOR gate. Now, what is the second input? Here, we are taking a common input as a second input to all the XOR gate, which is M. One common input we are taking as a input to the XOR gate. Now, your XOR gate is given with 2 input values. One is the bits of the register B and the second one is a common input which is M. Right? So now your full adder is having 2 inputs. One is A and the second one is the output of your XOR gate. What is the third input to the full adder? To this full adder, the third input is the output of your previous full adder. Output of the first full adder will be given as input to the second full adder. But what is the input to third input to the first full adder? That is C0. And in this case, your C0 is again equivalent to 1. Before this, let us see how this XOR gate is performed. XOR gate is operated. When you XOR any bit with 0, the result is the bit itself. When you XOR 0 with 0, the result is 0. When you are XORing 1 with 0, then the result is 1 itself. That means when you are XORing any bits with 0, the result is itself. In the same way, when you perform the XOR operation with 1, XORing with 1 will give you the complemented bits. So when you are XORing with 1, in these two cases, you are performing the XOR operation with 1. The result is what? The complement. That is complement of 0, it is 1. Complement of 1, that is 0. So this way XOR gate is performed. Right. Now see here. So we are using this circuit, this logic circuit we are using to perform both addition as well as the subtraction. When you are using only the full adders, you can only perform the addition operation. Here, when you are using the full adders with a combination of these XOR gates, you can perform addition as well as subtraction, and that depends on the value of m. That depends on the value of n. You can perform addition as well as subtraction. Right? Now, let us suppose if m is equivalent to 0, what will happen? If m is equivalent to 0, one of the input of this XOR gate is what? 0. One of the input of XOR gate is 0. And when you see the truth table of the XOR gate, when you XOR anything with 0, what is the result? The result is itself. 0 XORed with B0, it will give you again B0. 0 XORed with B1 will give you B1. 0 XORed with B2 gives B2. 0 XORed with B3 gives B3. That means one input to the full adder is A0. One input to the full adder is direct bits of the register A. What is the second input to the full adder? That is the output of your XOR gate. So when your M value is 0, what is the output of your XOR gate? The output of the XOR gate is the bits of the register B. So what are the two inputs? A and B. A and B. That means A plus B. Now what is this C0 value? C0 value is again equivalent to M. Here I have considered M value as 0. Therefore, what it will perform? This full adder will perform A plus B plus C0 as 0. A plus B means what? It is equivalent to addition micro operation. Therefore, whenever the value of M is equal to 0, this circuit acts like a binary adder. In the same way, whenever the value of M equal to 1, see how this logic circuit works. Whenever this value M is 1, this 1 is given as one input to the XOR gate, to all the XOR gate. Now, according to the truth table of the XOR gate, when you XOR anything with 1, the result is its complement. So, the complement is B0 bar. Here the output of XOR is B1 bar, B2 bar and B3 bar. So the two inputs to the F5 full adder are A plus complemented value of the register B. A plus B bar plus what is C0? Here C0 is equivalent to M. Here I have considered M as 1. Therefore C0 is again equivalent to 1. Now what is the resultant? A plus B complement plus 1. When you see the subtraction, you can implement the subtraction by using the addition. How you can implement? R2. The direct subtraction, it is equivalent to R1 plus R2 bar plus 1. Now, when you see this logic circuit, when value of n equal to 1, this logic circuit is acting like a binary subtractor. Right? So, based on the value of m, this binary adder subtractor will act like adder as well as it will act like a subtractor. I am going to end my session today. If you have any doubts, you can post it in the chat box. Some of you asked memory transfer. Memory is the storage component in your system. So when you want to perform any operation, you need to retrieve the data from the memory unit. Once the operation is done, if you want to store the data again, you can store it in the memory component. So the two operations that are associated with the memory are read operation as well as the write operation. Whenever you want to read or write, first you need to know the address of the memory unit, from where you are reading and into which location you are writing the data. The address needs to be known before you perform read and write. So here we are using address register. AR is the register used to store the address of the memory component. DR is the register used to store the data, used to store the content which is read from the address register. When you are performing the read operation, so first thing is what? First we should know from which memory location you are reading the data. So M of AR means this address will be given. If AR is 100, I want to retrieve the data present at location 100. M of 100. Whatever the memory word present at location 100 is to be retrieved. Whatever the data is retrieved, that will be placed in the data register. In the same way, in write operation, so you want to place the content of R1 into the memory unit. Right? So into which location of memory unit you want to place this R1's data, that address is to be known before you perform write. Right? So this can be represented as R1 tends to M of AR. If AR is some 200, then place the content of R1 into the location specified as 200 into 200th memory location. So the two operations that can be performed with read memory unit or read and write. When you perform read operation, then data will come out of the memory. When you perform write operation, you can write data into the memory. Next, AR is the address register. Address register means what? You need to specify into which location of this memory unit or from which location of this memory unit you are reading or writing the data. Next, some of you asked me about this full adder and binary adder. Full adder means it is a digital circuit. What this full adder will do? Responsible for performing the addition of only 2 bits. 2 bits that will also be included. Consider this as one register data. This is another register data. I want to perform addition of these two registers data. One. So what this full adder is doing? Full adder is responsible for performing addition of 2 bits. When you are considering two register, first register LSB data, second register LSB bit. So to perform addition of these 2 bits, and if there is any carry, that can also be included. So the addition of those 3 bits is done by using the full adder. So here to perform 1 plus 1, full adder is responsible. When you see the rules of binary addition, when you add 1 and 1, the sum will be 1 and it will leave a carry as 1. You ask me what is a carry. So when in general, when you perform the decimal addition, let us suppose if I have performed 9 plus 6. 9 plus 6 means what? The sum. When you are writing 9 plus 6, how you will write? 9 plus 6 is equivalent to 15. So that can be equivalent to 1 0 here. That 15 is equivalent to 1 0. That means 5 is your sum value and 1 can be equivalent to the carry value. Whenever you have more bits to be added, what you will do? Whatever the carry is generated after performing 9 plus 6, that carry will be added to the next bits for performing the addition. In the same way, here in binary addition also, if you have a carry, that will be included to perform the addition operation. 9 plus 6 means 5 is your sum, 1 will be your carry. Here also 1 plus 1 means 0 is the sum value, 1 is your carry value. So full adder is responsible for addition of these two bits, or if there is a carry, that carry is also included. Any other doubts? In the last session, you asked me the fourth question. In the last section, we have a quiz was conducted. In that, I have given the fourth question as how many multiplexers are required to construct a bus system of 16 register? To construct a bus system of 16 register, where the size of the register is 18. 1 second. I'll explain. See this example. Here, when you are constructing a common bus system, one way of constructing the common bus system is by using the multiplexer. When you are using these multiplexers, how many multiplexers are required? Number of multiplexers required to construct the bus is equivalent to the total number of bits in the registers. Number of multiplexers are equivalent to number of bits. And what should be the size of the multiplexer? The size of the multiplexer is equivalent to total number of registers. For the fourth question is, here I ask you to count the number of multiplexers required. So your number of multiplexers required is always equivalent to the number of bits in the register. What is the size of the register? The size of the register here it is 8. So the total number of multiplexers required is 8. So B is your answer. Any other doubts? As the time is 5:20, so can I continue for 40 minutes? If you are ready, we'll conduct the quiz. If not, the quiz will be conducted in the next session. I'll end up my section. I'll end my session. Okay. We'll conduct the quiz in the next session. Thank you.